Alright, let's go over a few examples to see if we now know how to apply the rule. Okay, so we are given this expression here for the first problem. We are asked to compute the limit of x cubed minus 8 over x to the fourth plus 2x minus 20 as x approaches 2. And here the first thing to do is to check the hypothesis. So check hypothesis. The most important one is to check that the top and the bottom either go to 0 or plus or minus infinity. So f of x here is equal to x cubed minus 8, which does indeed approach 0 when x approaches 2, and so does g of x, which is x to the fourth plus 2x minus 20, and this also approaches 0 as x approaches 2, because, well, if you just evaluate at 2, you get 2 to the 4th, which is 16, plus 2 times 2, which is 4, so you get 20 minus 20, that's equal to 0. So we're in a situation where we can apply L'Hopital's rule. And L'Hopital's rule then tells us that we can compute this limit here by taking derivatives of the top and the bottom. So x cubed minus 8 prime divided by x to the fourth plus 2x minus 20 prime, and that is equal to the limit as x approaches 2 of 3x squared divided by 4x cubed plus 2. And here at this point we can simply go ahead and apply our limit laws. So here the top and the bottom are both continuous functions, so the only thing preventing us from evaluating this would be if the denominator vanished at the point x equals 2. But this is not the case because when x is equal to 2, this expression is clearly non-zero. Okay, so we can just go ahead and evaluate now. So we get 3 times 2 squared divided by 4 times 2 to the cube plus 2, which is equal to 12. 2 to the cube is 8. 8 and 4 is 32 plus 2. So we get 34. So 12 divided by 34. And that's the final answer. So the second problem, let's compute a limit when the point A is not equal to 0. Because I don't want to give the impression that whenever you ask to use L'Hopital's rule, the point that x is approaching is 0. So again, we have to check the hypothesis. So cosine, so f of x here is cosine squared of x, which approaches 0 when x approaches pi over 2. Cosine of pi over 2 is 0. And g of x, which is 1 minus sine x, is also approaching 0 when x approaches pi over 2, because sine of pi over 2 is 0. Okay, so we check the hypothesis basically. Well, the derivative of the denominator is non-zero on near pi over 2, not at pi over 2. Remember, when we are computing limits, we never care about what happens exactly at the point just nearby. Okay, but we've checked that they're both numerator and denominators tend to 0 as x approaches the point pi over 2. So we're safe to apply L'Hopital's rule. And then we get that this is equal to the limit as x approaches pi over 2 of the derivative of the top, which is 2 cosine x times minus sine x. We're applying the chain rule, divided by the derivative of the bottom, which is minus cosine of x. So we can cancel the cosine of x and the plus and minus, no, the minus signs here. Okay. Okay, so and finally we get 2 times sine x divided by 1. And well, that's a continuous expression, so we can plug in pi over 2 for x, and we get 2 times sine of pi over 2. Sine of pi over 2 is 1, so we get 2 times 1, it's just 2. So that's our answer. And what about this example? Well, let's check the hypothesis here. So there's two hypotheses that involve, well, what the numerator and denominator are approaching to, and also that the derivative of the denominator doesn't vanish near the point, the denominator. Okay, so what happens here? So sine of 5x approaches 0 as x approaches 0, but x cubed minus 7 is approaching minus 7 as x approaches 0. So L'Hopital's rule does not apply. Right? Because even though the numerator is approaching 0, the denominator isn't. But luckily then, we can just go ahead and compute the limit, because both expressions here, so the numerator and the denominator, are both continuous functions. And as we learn, whenever we have something like that, we can just go ahead and evaluate, except when the denominator is 0 at the point, which in this case isn't, because it gives you minus 7. So we can just go ahead and evaluate. So everything here is continuous and everything here makes sense. So we can evaluate, evaluate the limit by simply evaluating the expression inside. So this is sine of 5 times 0 divided by 0 cubed minus 7, which is just 0, divided by 7, which is 0. Okay, so this is the answer. But so, if you had tried to apply L'Hopital's rule, you would obtain cosine of 5x cosine of 5x times 5 divided by 3x squared, and that would not be defined, I mean, would not lead you to anything that had a limit. Okay, so you're dividing by something that's approaching 0, and while the top is approaching a constant. Okay, so that would be incorrect. So always check hypothesis first before applying the rule. So okay, so that is all about the we need to know when dealing with quotients. But we need to, as we said in the previous video, we can apply the rule to other forms. One of them, the most common one, is form 0 times infinity. There's a canonical example again, one from the book. What happens if we're asked to find the limit of x, natural log of x, as x approaches 0 plus. So when as x approaches 0 plus, x approaches 0, and natural log of x approaches minus infinity. Okay, so we're in a situation where we have something that is getting very small and something is getting very negative. So which effect is winning? We don't know. So we need to write this down in a way in which we can apply L'Hopital's rule. So what are we going to do? So x times natural log of x is the natural log of x divided by 1 over x. Okay, now this here is approaching infinity as x approaches 0 plus. Well, the top is approaching minus infinity. Okay, so and this happens when x is approaching 0 from the right, because this is a situation that is suitable for L'Hopital's rule. So applying L'Hopital's rule, we get that this is equal then to the limit as x approaches 0 plus of what is the derivative of natural log? 1 over x divided by the derivative 1 over x, which is minus 1 over x squared. This is the same as the limit as x approaches 0 plus of minus x. Remember, if we have 1 over, say we have something like 1 over x divided by minus 1 over x squared, this is the same as 1 over x times minus x squared over 1. So this is where we get this expression here from. Okay, and the limit here, one of minus x as x approaches 0 plus is simply 0. Okay, so this is the limit here. So again, whenever you're dealing with the forms 0 times infinity, you need to write this down as a quotient. So you have a product, so write it down as a quotient. Something going to infinity divided by something going to infinity, as in this case, or something going to 0 divided by something going to 0. So that you can apply L'Hopital's rule. Now there's a warning I have to make. So it will often be the case when you have to decide, because here you have another option. Instead of writing this as natural log of x over 1 over x, you could have here's a remark. One could have rewritten x times natural log of x as x times 1 over the natural log of x. But in this case, if we applied L'Hopital's rule, this is a perfectly legitimate form, because here x is going to 0, and as natural log is approaching minus infinity, 1 over minus infinity, well, 1 over something really negative is approaching 0 as well. And this happens as x approaches 0 plus from the 0 from the right. Okay, so we could apply L'Hopital's rule. Apply L'Hopital's rule and get the limit that we want to compute, namely x times log natural log x is the same as the limit x approaching 0 plus of x over 1 over natural log of x, which would be equal then to, according to L'Hopital's rule. So here we'll be applying L'Hopital's rule. Equal to 1, which is the derivative of x, divided by minus 1 over natural log of x squared. Remember, because we have a composition of two functions, we need to apply the chain rule, times the derivative of natural log. And what is the derivative? The derivative of natural log is 1 over x. So this is the same as the limit as x approaches 0 plus of minus x times the natural log of x squared. Well, in fact, all we've accomplished here is to make our expression more complicated than the one we started with. So here we have minus x times natural log of x squared, while what we started with was x times natural log of x. So this is not very good. Okay, so what is the remark here? This is true. I mean, you can apply L'Hopital's rule. The only thing here is that what you get is not easier, or does not lead you to any value. So you need to apply L'Hopital's rule again and again, and you will get increasing powers of natural log, and will be a mess. So this will not be very useful. So whenever you have to compute, so the advice here is that whenever you have to compute limits of expressions that involve the natural log and x, just leave the natural log alone. So when you need to apply L'Hopital's rule to expressions involving natural log of x and need to rewrite the expression as a quotient, leave the natural log of x as it is, and rewrite the rest. Rest is what you need to move around. So look at this example. Here we had x times natural log of x, so we kept the natural log of x here. Oh, sorry for that. So we kept the natural log. Okay, so the natural log of x remained where it was, and we just move x. X we rewrote it as 1 over x. Okay, and that was what led us to the final answer, which is 0. If instead we had rewritten the natural log of x as 1 over natural log of x, then we would not get the answer we wanted. So always do as we did in our first try. Natural log of x just remains as natural log of x. Just move the rest around. So x needs to be rewritten. Okay, so we do that then. We write x as 1 over x. Okay, so that's the advice. Okay, we'll see a few more things in the next video, and then we'll conclude the section on L'Hopital's rule.